Hey, welcome back, everybody. We've got another mega Calc 2 integral. This integral features Pythagorean identities, double angle formulas, U substitution, partial fraction decomp, and the natural log function. Great problem for reviewing a lot of ideas in one rich example. Okay, so let's quickly talk about what we're going to need to solve this. So I'll say, of course, recall the following. So of course we're going to need that cosine squared of theta plus sine squared of theta is 1. That's a classic. But we also want to recall some double angle formulas. So we want to recall that, let's say sine of 2 theta, well, that's exactly 2 times cosine theta times sine of theta. Of course, I could write that in the other order, 2 sine cosine, both of theta, by commutative law of multiplication. Okay, so for number 3, we're going to need the cosine of a double angle. And that's exactly the cosine squared of theta minus sine squared of theta. So that's going to be helpful. And so what else do we need here? And I think for now, oh, here's something we're going to need. We're going to need the idea that if I take any constant, then k is equal to k times cosine squared of theta plus sine squared of theta. That's really just saying that k is equal to k times 1, which might seem obvious, but sometimes we forget that we have the sort of flexibility to think about a constant in this way. And then we'll talk about the partial fraction decomp as we encounter it, and then we'll recognize the natural log function, right? So of course we know that this is the natural log of the absolute value of u plus c. Okay, so I think without further ado, we're going to go into the integral. And I think you'll enjoy this one. That was kind of fun. Okay, so we've got the integral of dx over 3 sine of 2x plus 2 cosine of 2x plus 3. And so here's where I want to sort of think about using some formulas, right? So in this context, sine of 2x, I could think about this as 2 cosine of x sine of x. So we mentioned that before. We just want to have this handy. And then cosine of 2x, we mentioned before, that's exactly cosine squared of x, but minus sine squared of x. And then here we've got a constant. It might be helpful to think about this constant as 3, which is 3 times 1, and 3 times 1 is really 3 times cosine squared of x plus sine squared of x. So that's a little trick you can take with you. It's nice for solving certain problems. And so with this, let's go ahead and make some substitutions here. So using a lot of identities, it's going to give us the following. So I'm going to have 3 times this quantity, right? So if I take this and multiply both sides by 3, that should give us a 6 cosine of x times the sine of x. And then here, I want to take this and distribute a 2, right? So if I go here and I distribute a 2, that should give me a plus 2 cosine squared of x minus 2 sine squared of x. So again, I just went to this formula and multiplied everything by 2. So if I multiply both sides by 2, remember to distribute, you get this. And then here's the part where we're really clever here, right? We're thinking about 3 in this way. So distribute the 3. So that's 3, looks like 3 cosine squared of x plus 3 sine squared of x. Okay, so at this point, we want to go ahead and combine like terms. And so where do we see some like terms? Let's see here. So with cosine, so 2 cosine squared of x plus 3 cosine squared of x, we can combine those. What else do we have here? So these are like terms, so we'll combine those. And this I can just leave. All right, so let's see what we have here. So this looks like, you know what, we could just write it in this order. This is just fine. So 6 cosine of x sine of x. And then this plus this means I've got 5 copies of cosine squared, right? So that's 5 cosine squared of x. And this plus this means I've got one of these sine squareds of x. So plus 1 sine squared of x. And so you might look at this and say, well, what on earth can we do now? Well, sort of taking inspiration from the previous video, right, the mega Calc 2 integral number 1, let's go ahead and multiply the top and the bottom by 1 over cosine squared. And we're hoping some relation between tangent and secant pops up. So in terms of problem solving, this is the part in the background that, maybe you wouldn't see. This is where the struggle happens, where you try a whole bunch of different things and you finally arrive at something that's fruitful, that works for you. Okay, so that's sort of the helpful trick. So yeah, I multiply by this useful form of 1. And let's see what we have up top. Well, I know that 1 over cosine squared, that's exactly secant squared, right? So I'm going to call that secant squared of x up top. And that's dx. And then let's see what's happening downstairs. Okay, so it looks like one of these copies of cosine will cancel. In fact, just to be more detailed, let's show this. So I've got 6 cosine of x sine of x. And when I distribute this to the first term, I'm going to be kind of clever about the way that I split this up. So I'm going to think about it like this. So I'm going to think about it like this times this. It's still cosine squared, but grouping it in this way is actually pretty helpful because these will cancel, right? And then you're seeing tangent. And we were hoping to get some sort of relationship between secant squared and tangent going on, so we can do a substitution. So that seems good. That takes care of the first term. So it was this times this. So now this times this. This is 5 cosine squared of x. Looks like over cosine squared of x. So that's really handy. That's going to cancel out to give me a 5. And then right here, this is really promising because I know that sine over cosine of the same angle is tangent of that angle. So yeah, that seems really good. So yeah, pretty happy with that. Pretty happy with that. Okay, so yeah, let's simplify this. Okay, so those will cancel. That's going to give me 6 tangent of x. So that's really nice. And that's going to give me plus 5, it looks like. And that's going to give me a tangent squared of x. Okay, so that seems really good. Let's use a u substitution. Let's let u equal tangent of x. And I know that's going to be helpful because when I take the derivative, that gives me exactly secant squared of x dx. That means for this choice of u, this will take care of this. So I get all of this in terms of my new substitution variable u, so I'm pretty happy with that. That makes me really happy. Okay, so what does this look like now? So upstairs is just du. Well, that's really nice. downstairs, that's going to be 6u plus 5 plus u squared. But that looks like a quadratic, right? So let's get that in descending order of exponents, and we'll think about how to tackle it. We're either going to have to factor or complete the square, so we'll sort of mentally be ready for both. Okay, cool. So descending order of exponents. But this splits really nicely, right, into the product of two binomials. So this is exactly this. So it looks like u plus 1 times u plus 5. And we can check that. So we've got u squared. Product of the outers plus the product of the inners is 6u. And then this product is 5. Okay, great. So this is telling me, because I've got the product of linear factors, to consider partial fraction decomposition. So this technique of partial fractions is really handy. So not only do we use it in Calculus 2, but you'll see it again in ordinary differential equations, and down the road even further if you end up taking a course called complex analysis. So very, very handy. And so what I'm going to do is sort of put this on hold, put this integral on pause, because I want to do some algebra. I want to split this into the sum of two fractions. That means each piece will be easier to integrate. So I want, little bite-sized fractions. So we're going to put this on pause. It's algebra time. And so I've got this. And the one thing I want to notice is that both of these factors are linear and unique, right? They're not repeating, right? So this is linear and unique. This is linear and unique. So remember how to decompose linear unique factors? I need a constant over the first factor plus another constant over the second factor. Our goal is to solve for a and b. If I'm able to do that, that means I can break this into little bite-sized pieces. So that seems really promising. So the first thing we want to do is get rid of the fractions here, right? So I'm going to multiply. So let's multiply everything by u plus 1 times u plus 5. It's going to kill the fraction, make it a little bit easier to find a and b. Okay, so imagine distributing and canceling where appropriate. Okay, so this over this is 1. That seems nice. And then, if I have this times this, imagine what would cancel out here. So those would cancel out. So goodbye. I'd be left with a times u plus 5. And then over here when I distribute, so you can see that the u plus 5s will cancel, and I'd be left with b times u plus 1. So in particular, if we look at this equation, so I'm not necessarily looking here now. So if I look here, so remember how to sort of interpret an equation like this. It means this is true for any choice of u. So if I pick a choice of u, say I pick u is 10, for example, right? If u is 10, as long as I plug that into all the u's here, that's still true because this equation holds for any fixed choice of u. If that's the case, if this holds for any choice of u, why not pick really convenient choices? So for example, if I wanted to solve for a, if I choose u is equal to minus 1, which is legal as long as I plug that into all the u's, I can find a. So I'm going to say that. I'm going to say if u is equal to minus 1, then by plugging minus 1 in for all of the u's, that's going to give me 1 is equal to, let's see here, minus 1 plus 5 is 4. And so that implies that a is 1/4 or a quarter. So that's nice. And that all hinged on the fact that this is true for all u. Again, I'm not necessarily looking here, I'm looking here. Okay, so sort of keeping in that spirit, let's say we wanted to solve for b. If I want to solve for b, what choice of u here would make this vanish so I could get my hands on b? Well, if u is -5, this will vanish. That would allow me to find b. So if u is -5, we have the following. 1 is equal to, well, that's going to vanish, and that should be -4b, and that implies that b is -1/4. So that's good. So since we're able to find a and b, that means we can rewrite this in terms of the integral of this. And so our original integral can be thought of like this. So a we said is a quarter. Don't let that fraction bother you. Right? It's just some constant. We can factor constants in front if we want. Over u plus 1. So that's a over u plus 1. So a over u plus 1. And then b we said is -1/4. I'm going to write it like this. Right? So -1/4. And then b goes over u plus 5. That'll be du. So I'm hoping at exactly this point you recognize some natural log forms because the denominators, the variables are to the first power, right? So that means I've got 1/4 times the natural log of absolute u plus 1 minus 1/4 times the natural log of absolute u plus 5, of course, plus c. Okay, so of course we could use log rules to, write this as a single logarithm if you wanted to. I'm going to opt not to, but if you want to simplify, that's just fine. We just want to remember what was u equal to. So from before we said u is equal to tangent of x. So this is the tangent of x plus 1. So minus, I've got 1/4 times the natural log of absolute. Tangent of x plus 5 plus c. Such a cool integral, reviewing tons and tons of Calc 2 ideas, little trigonometry in there. I hope you enjoyed.